So yesterday we finished off by analyzing the starter model flavor structure and the pattern of the flavor symmetries in the starter model and their breaking. So today we're going to start off by analyzing the phenomenological consequences of this. And to do this, we'll first write down the starter model weak interactions in the mass basis. So yesterday we wrote down everything in interaction basis, where interactions were universal. Today we're gonna go to mass basis, where the Yukawas are diagonal, and we'll start with that. So we'll analyze the mass basis. Okay, so how do we get there? So we start with the vacuum state, where the neutral component of the real neutral component of the Higgs doublet gets a VEF. So in the unitary gauge, we can write the following replacement. Okay, and then the Yukawa interactions will give rise in this minimum, the Yukawa interactions will give rise to Fermion mass matrices. So we can write a quark mass matrix, for example, as V over square root of 2 times the corresponding Yukawa matrix. So the mass basis, by definition, then corresponds to a basis where these mass matrices are diagonal, or corresponding to the Yukawa matrices are diagonal. Starting from the interaction basis, we can switch to the mass eigenbasis via unitary transformations on the fermionic fields. So we can write down unitary transformations between any two bases of fermionic fields. In the following, we can transform all the fields. So the left-handed quark doublets are rotated with the matrix unitary matrix VQ. The right-handed up type quarks with unitary matrix VU, and the down type right-handed fields with unitary matrix VD. Okay, so any such unitary transformation on all the fermionic fields will, of course, leave the gauge kinetic terms variant. What happens to the Yukawa matrices? So extracting the corresponding Yukawa transformations from the Yukawa terms, we see that a up-type Yukawa in a given basis after the rotation is given by VQ times YU times VU Hermitian conjugate, and corresponding the down-type Yukawa matrix is transformed as VQ YD YD Hermitian conjugate. Now, since the Yukawa matrices are arbitrary complex matrices, their diagonalization requires biunitary transformations. So in particular, we can say that we can require that a given VQ with a superscript U times mu, which is just the Yukawa matrix YU times V over square root of 2, times VU dagger, we require this to be diagonal. Okay? And we can write it then as V over square root of 2 times lambda u, where I defined lambda u as the diagonal matrix with the diagonal entries being yu, yc, yt. Similarly, I can do a similar rotation diagonalizing the down type Yukawa, but now, of course, in general, I will require a different unitary transformation on the left. VD, how did I write it here? VD Hermitian conjugate. Again, I require this to be a diagonal matrix, which I can write then as V over square root of 2 times lambda d, where again, lambda d has the diagonal entries yd, ys, and yb. Now, VU and VD are unphysical in the standard model, simply because they leave all the other terms except the Yukawa terms completely invariant. Okay, so you can do these rotations and you can check explicitly that all the other terms containing fermions remain invariant. So let me write it here. So VU and VD are unphysical. However, this is not necessarily true for VQU and VQD. Namely, in general, the mass matrices for up and down quarks were not commute. So in general, they cannot be diagonalized in the same basis. Which means that this combination VQU times VQD Hermitian conjugate, which we will denote as VCKM, will not be equal to the identity. Okay, so let's check this explicitly by just writing out the gauge interactions of the fermionic fields in the mass basis after performing these rotations. So this will be the fermionic standard model Lagrangian in the mass basis, LFM. And we can split now the neutral current interactions from the charge current interactions and write the neutral current interaction the following way. Qi bar d slash Qj times delta ij with the subscript nc denoting neutral currents, meaning that here Qi and Qj will be either up quarks or so either both are up quarks or both are down quarks. I and j are Flavour indices, and again I'm explicitly writing out the Kronecker data to explicitly show that these interactions are Flavour diagonal and universal. Okay. So here NC denotes neutral currents, meaning interactions with gluons, photons, and the weak Z boson. But then we have an additional term, which is the charge current weak interactions, which now can be written as ULI bar gamma mu Vij CKM DLJ W mu plus. Okay, so here, since the rotation of the left-handed fields into the mass bases requires different unitary rotations for up and down quarks. When I perform this, this CKM matrix appears in charge current weak interactions, and only in charge current weak interactions. These are, of course, not all the fermionic interactions in the star model. In addition, we have the Higgs interactions. So we can write down UL I bar lambda U ij UR j times V plus H bar square root of 2. Okay, where lambda U is the diagonal Yukawa matrix. Since we are in the mass basis, the Yukawa is diagonal. And the first term in the bracket will give the mass of the U quarks. The second term gives the Flavour diagonal but non-universal Higgs interactions with star model up type quarks. And we have a similar term for the down type quarks, DLI lambda D ij drj V plus H naught over square root of 2. Okay? Plus the Hermitian conjugate of these terms. Okay, so there are two types of Flavour interactions in the star model. We have the Flavour diagonal but non-universal Higgs interactions, and even more interesting, we have a single source of Flavour conversion or Flavour change in the star model, which is appearing in charge current weak interactions. So let's analyze these Flavour interactions in the star model in more detail. So how can we test this model of Flavour, which is the star model Flavour? So this would be testing the CKM. So the CKM matrix is the only source of Flavour in the star model. So when we talk about Flavour conversion in the star model, it has three particular features which may not persist once we go beyond the star model, and this is typically a problem for models beyond the star model. So Flavour conversion in the star model, firstly, it only proceeds through the three CKM angles. Okay. So the CKM, remember, is parameterized. So Flavour conversion in the star model is parameterized by 4 parameters, 3 angles, and a CP volating phase. We'll come to the CP volating phase a bit later, but when we talk about Flavour conversion, there are just the 3 CKM angles, which parameterize the unitary CKM matrix. So this is first particularity. So there is this single source of Flavour conversion. Secondly, Flavour conversion in the star model is, as you see, there is a single term. So it's only mediated by charge current interactions. So charge current interactions. So only electroweak charge currents. And the third particularity is that these charge currents only involve left-handed fields. Involve left-handed fields. Okay, so these are the 3 features that we have to look for and try to test as precisely as possible with experiments. Before doing so, let's first see how we can parameterize the CK matrix, because as you know, a unitary matrix has more parameters than there are physical flavor changing parameters in the star model. So apparently there is some redundancy in how we can parameterize the CK matrix, and let's explore the possibilities. parameterization of the decay. So a general parameterization is of course the most general one is written here. So we have 9, in principle we have 9 complex parameters. This would be a general 3×3 matrix, right? But of course, since it's unitary, and furthermore it only has one phase involved, there's a huge redundancy in this way of writing it. But there is an additional ingredient that is very useful in that we know from experiment that the entries of the CKM are far from generic. In fact, they are highly hierarchical. So the CKM is close to an identity matrix. Okay? So we can actually, it's a useful way to parameterize it is in terms of small departures from the identity matrix. So let me check if I have this here already, so I don't write all of this down. Yeah, okay, so a general way to parameterize a unitary matrix with 3 angles, so with 3 angles and a single phase is this way. So of course this is not a unique way, it's just one parameterization which was in particular adopted by PDG. But this parameterization, although it's manifestly in terms of 3 angles and a phase, does not really use the fact that the diagonal entries in the CKM are close to 1. So roughly, we can see that the diagonal entries are close to 1. The 1, 2, and 2, 1 entries are roughly 0.2. The 2, 3, and 3, 2 entries are roughly 0.05, let's say, or 0.04. So 0.2 squared. And the 1, 3, and 3, 1 entries are of the order 0.007, let's say. 0.007. So again, roughly 0.2 cube, okay? So a useful way to think about this, or here I've written 0.05, okay, 0.05. So a useful way to think about it is that there is a parameter which is of the order of 0.2, where the 1, 2, 2, 1 entries are of the, or let's call it lambda, will be of the order lambda, the 2, 3, 3, 2 entries will be of the order lambda squared, and the 1, 3, 3, 1 entries will be of the order lambda cube. And this fact is used by the so-called Wolfenstein parameterization, where in fact we define these, so in the PDG parameterization, you will see the C's and the S's denote the sine and cosines of angles. So C12 defines the cosine of the 1, 2 angle, if you want. And respectively, the S12 is then the sine of this same angle. And the same for 1, 3 and 2, 3. Okay? But now using this hierarchical, empirically known hierarchical structure of the CKM, we can just define, so the S12 which enters in the 1, 2, 2, 1 entries, we just define it as lambda, okay? And similarly, the S23, we define it as order lambda squared, but of course it will not be exactly lambda squared, but some parameter times lambda squared. So it's some parameter which is in principle order 1 times lambda squared. And then finally, the S13, which I told you should be of order lambda cube, in fact, is defined as being a times lambda cubed, but now we need to take into account the Cp evaluating phase. So in addition to this, we say, okay, this S13 times this phase e to the I delta is just this order lambda cube parameter times a complex number of order 1, which we parameterize with two numbers, rho minus I eta. Okay? So in this parameterization, there is a single expansion parameter, which is lambda, and two real and one imaginary parameters of order 1, and in this way it remains completely general. Okay, so by doing that, you can always do this reparameterization, and it's still exact. Okay, so and you can do now once you have this identification, what you can do now is you can systematically expand in lambda, and to each order in lambda, this parameterization will remain unitary, which is important. Okay? So in particular, here I've written out such an expansion up to order lambda cube, and nowadays, since the precision of experiments has reached a certain level, one actually needs to use expansion up to order lambda to the fifth, and this is the parameterization in the expansion of the CKM in the Wolfenstein parameterization up to this order. Okay? So some terms are actually exact even up to high orders. Okay, so finally for so let me see. Okay. So the first thing that is useful to check when we try to test whether the CKM is the only source of flavor conversion and Cp evaluation in the flavor sector in the standard model is to test the unitarity of the CKM. So let's write the unitarity conditions. So in general, you can write unitarity constraints on the CKM by basically writing so when you write down the unitarity relation, V dagger V is 1 or VV dagger is 1, is the identity matrix. So you can, for each term in this, in this 3x3 matrix that you get, you can write a single unitarity condition. So you have 9 conditions in general. Okay? In particular, you can write down the terms on the diagonal and the off diagonal. So the diagonal ones will require to be 1 and the off diagonal 0. So in general, you can write down the following relations between rows and columns of the CKM. So V star ik, vjk, summed over k, needs to be equal to delta ij. This is a unitarity constraint on the columns, and similarly for the rows, sum over k, vki star vkj equals again delta ij. So we have these two sets of unitarity constraints. And it turns out that since the CKM is very hierarchical, the values of the terms, so each of these is basically a sum of 3 numbers. And since the values of the CKM elements are very hierarchical, it means that for most of these conditions, 1 or at most 2 terms will completely dominate this sum. Okay? So for example, if one of the if we think about the 1, 1, so I and j equals 1, we know that the first two columns and rows will completely dominate over the third one, because the off-diagonal entries to the third, mixing the first with the third generation, are very tiny. Okay, so the most interesting conditions are the ones where all the terms in these sums are of the same order, and it turns out this is particularly true if we fix I equals 1 and j equals 3. So let's write this unitarity condition out explicitly. So this means that we get the following sum: VUD times VUB star plus VCD times VCB star plus VTD times VTB star equals 0. Now you can check that all of these terms in the sum are of the same order in the lambda expansion. Okay. So all terms of same order in lambda expansion. It's particularly useful to write this to rewrite this unitarity condition by dividing everything with the first term, second term, sorry. We divide everything with the second term, and we can write out the same unitarity condition as VUD, VUB over VCD, VCB star plus VTD, VTB star, so there's a star up here, over VCD, VCB star plus 1 equals 0. In this way, we've completely removed the dependence on lambda, because all the terms are of order lambda cubed. So when we divide by one of the terms, all of the terms become order 1. Okay, so now we are comparing 3 complex numbers of order 1. Okay, one of them being just 1. Okay, so if now I just replace these ratios with the Wolfenstein parameterization, it turns out that this can be written out as rho bar plus I eta bar plus 1 minus rho bar minus I eta bar minus 1 equals 0. And again, this relation, you can check it's manifestly true, okay, in the standard model, because the standard model is unitary, and the Wolfenstein parameterization remains respects unitarity order by order in lambda. So since everything was expanded in the same order in lambda, it retains, it respects unitarity. And so this relation is valid up to order lambda to the 5th, as it's written out, where I've just used a singular replacement of rho and eta with the rho bar and eta bar, which is just the rho and eta multiplied by 1 minus lambda squared over 2. So if we have a sum of 3 complex numbers which sum up to 0, this defines a equation of what kind of object in a complex plane? It's a triangle, exactly. So this actually defines a triangle in the complex plane. So let us visualize it. And the parameters which enter are rho bar and eta bar. So we don't have any dependence on A and lambda in the particular relation once we've summed up the lambda squared correction into the quantities rho bar and eta bar. So in terms of rho bar and eta bar, so eta bar parameterizes the imaginary component and rho bar the real component or dimension. And so one side is just 1, okay? So on the real axis, one side of the triangle I can just set as 1, so this would be one side of the triangle, okay? And then the apex of the triangle will sit at the value rho bar eta bar, okay? So this will be the apex, and then I can define this triangle, okay? So this is the rho bar eta bar star model, okay? Now, in this triangle, there are several quantities that are observable and measurable, and these are the angles of the triangle, so which are conventionally defined as alpha, beta, and gamma, or phi 1, phi 2, phi 3. And remember, whenever you see, so there are two ways to parameterize it in the literature, either with alpha, beta, gamma, or phi 1, phi 2, phi 3. Remember that alpha is not phi 1, okay? I always forget the matching between those two, but you just need to look it up. I mean, I will consistently use alpha, beta, gamma, so there is no confusion. But sometimes you will also see phi 1, phi 2, phi 3, and the matching is not trivial. So these are the angles. In addition, we can also measure the sides of the triangle. So the length of the sides. So both angles and sides of this triangle turns out to be invariant under any reparameterization of the CKM, so any unitary rotations on the fermionic fields which leave mass bases intact, and so they are measurable quantities. Okay, so angles and sides are measurable quantities. Remember, a particular element in the CKM in general is not a measurable quantity because it's not invariant under reparameterization, because there is arbitrariness in how we parameterize the CKM. But the angles and sides of the unitary triangle, they are measurable. Okay, so let's see how we can gain access to them. So first, we need to measure the quantities which do not enter directly into this particular unitarity triangle, but are needed as inputs to define the CKM. In particular, those are the lambda and A parameters of the Wolfenstein parameterization, or in terms of the moduli of the CKM elements, which are measurable quantities. These are can be extracted from measurements of the moduli VUS and VCB, and those can be measured from semi-leptonic kaon or B decays. And on the right, you see I think those are fairly up-to-date values of lambda and A extracted from such measurements. Okay, so those are just decay rate measurements. Okay, nothing more sophisticated. So the first non-trivial constraint in this particular unitarity plane comes from a measurement of the modulus of the VUB CKM matrix element, which can be extracted from semi-leptonic, so CKM suppressed semi-leptonic B decays. So this corresponds to, at the quark level, this would correspond to a decay of a B quark to a U quark, a charged lepton and a neutrino. So we B to U L nu decay. And the decay rate of this, of course, is proportional to VUB, okay? It's absolute squared. So VUB absolute squared is you can check that it's proportional to rho bar plus eta bar, rho bar square plus eta bar square, which defines a circle in this plane around the origin. Okay, so you can, since this measurement has an uncertainty, this defines then a band, a circular band in this plane. And this is roughly the currently measured value. Okay. The second observable, which I will discuss in a few minutes today, so still today I think, if not in the morning, in the afternoon, is the Cp Asymmetry, which is parameterized the observable S psi k short. So this is measurement of what we call indirect Cp evaluation in the decay of B0 to psi and k short. Okay, psi is the J psi, Cc bar is the lowest lying Charmonium state, a vector Charmonium state, and the k short is the short-lived neutral kaon state. Okay, and so this we will derive this relation a bit later. So let me just say that this asymmetry is given exactly by the sign of the 2 beta angle. And then the beta angle up here, you can then express it again in terms of eta bar and rho bar, and has this expression. This is not difficult to check. So it, since it has a twofold solution, you get 2 bands in this plane. Okay, from a measurement of this quantity. The next constraint comes from a measurement of the gamma angle. Okay, we'll also derive how we can measure gamma a bit later, but let's just say that the measurement of the gamma angle, or the phase gamma, the Cp evaluating phase gamma, you can express it easily in terms of, again, rho bar and eta bar. And it has this form, and the current measurement, so this is a measurement which we usually denote as measurement of direct Cp evaluation, so Cp evaluation in decays, and in particular gamma is extracted from B charged B meson decays to D mesons and kaons, just from rate measurements, and the current precision is shown in the plot, and now we already have 3 measurements. So you know that once in such a triangle, having 2 measurements already defines the apex. So since we need to fix just rho bar and eta bar, so having 3 measurements already provides a constraint. So now with 3 measurements, we already have a non-trivial constraint on the CKM, and they of course luckily overlap, so it's consistent. But we can have many more measurements that are being performed. For example, one can also measure the third angle, alpha, which is extracted from B decays to pions and rho mesons. And the measurements of alpha, in particular, they define a non-trivial contour in this plane, shown in blue. Finally, the measurements of neutral B and B sub S meson oscillation frequencies, they will derive this relation. They're proportional, so the ratio of those frequencies is proportional to the ratio of VTT over VTS modulus squared. And again, you can express now this in terms of rho bar and eta bar, and this defines another circle around the 1, 0 point in the rho bar eta bar plane, which is shown in orange. And finally, we can also use kaon decays, in particular the measurement of direct Cp evaluation in kaons. So actually the observable which was the first indication of the presence of Cp evaluation at all, so epsilon k, also forms, of course, a constraint in this unitarity plane of the CKM. The expression for epsilon k in terms of rho bar eta bar is a bit more involved and lengthy, so I didn't even write it down because it's not very illuminating. But you can work it out, and it forms a non-trivial contour, which you see in pink in this plane. And so you see now I've listed here 1, 2, 3, 4, 5, 6 independent constraints, independent measurements, which all probe different relations between rho bar and eta bar in the standard model, and they all have a consistent overlapping region in the rho bar eta bar plane, and from which now we can extract the standard model values of rho bar and eta bar, which are shown below. So what are the main takeaways from this exercise? Is that, first of all, you see that so both parameters, rho bar and eta bar, are not exactly order 1, so they are a bit smaller than 1, but they are not much smaller than 1. In particular, the eta bar, you can say it's order 1, and the eta bar is the one parameter in the CKM which parameterizes the presence of Cp violation. Okay? It's the one imaginary parameter in the Wolfenstein parameterization, and it's in fact order 1. So Cp violation in the flavor sector actually order 1. The phase is order 1. It's not small. Okay? So the first takeaway is that the CKM phase is order 1. And the fact that the Cp violation experimentally or phenomenologically suppressed has to do with the smallness of the sides of the CKM matrix. Leads to the smallness of Cp violation. It's not not the smallness of the phase itself. Okay. The second important takeaway is that since all these measurements, which are sensitive to Cp violation and to the rate, the flavor conversion rates in the standard model, are consistent to a fair degree, we can conclude, and since many of these measurements have reached a precision which is considerable, so we can, for example, determine rho bar and eta bar to a precision better than 20% with consistent set of measurements, tells us that very likely Cp violation in flavor changing processes is dominated by the CKM phase. Okay, so the second thing that we can do before moving on to the details, how we actually derive these constraints from experimental measurements. Let me briefly connect the presence of this CK and Cp violating phase to the Yarlskog invariant, which I discussed yesterday, which is a parameterization invariant way of specifying the invariance or breaking of Cp violation, basically the presence of Cp violation in the standard model. Okay? Remember yesterday we wrote it down as the imaginary part of the determinant of the commutator of the squares of the Yukawas. Okay? But we can also do it in terms of physical quantities, so in terms of CKM elements and quark masses. So we can write down a parameterization invariant measure of Cp violation in the CKM. Parameterization invariant measure of Cp violation in the CKM. In particular, the imaginary part of any combination Vij, Vkj, where we sum over j, and VKL, VIL. Well, we sum over also over A, so we sum over all I, J, K, and L in such a combination of CKM elements. This can be shown to be to be equal to a number, JKM, times a sum of NN epsilon IKM epsilon JLN. Okay? And we can choose, so we can choose any IJKLN and we'll get the same number. Okay? And we can write it down explicitly. So we can choose any of these, and express it, for example, in terms of the Wolfenstein parameterization. And in this parameterization, this will be equal to lambda to the 6 a squared eta. Okay? So what this means is that, first of all, the smallness of CP violation is in fact due to the smallness of lambda, so the hierarchical almost diagonal structure of the CKM. So CP violation is suppressed by small mixing, flavor mixing. Small mixing, and of course it's proportional to eta, which is the, yes? No, sorry. No. There was a mistake. Yeah, here we don't sum. We sum over Mn on the other side. And these are just the completely symmetric 3-index tensors. Yeah. So we can actually choose any I, J, K, and L. Okay? And we get the same number for anyone, because it's a invariant measure of CP violation. Okay? And now if we do it explicitly, the numerical, so we plug in the values of lambda, A, and eta, we see that this is of the order 10 to the minus 5. Okay? So it's a small number, but it's small because of the hierarchical structure of the CKM. And now we can relate this JKM to the Yarlskog invariant. So the Yarlskog invariant J can then be written as JKM times the product of all pairs, flavor pairs, where I is bigger than J, mi squared minus mj squared over v squared. So a product of differences of mass squareds of quark masses. And since in this product we see that all the mass square differences enter, this will be suppressed by the smallest masses in the system. And we can evaluate it explicitly, and we get that this Yarlskog invariant in the standard model is always of the order 10 to the minus 22. Okay, so it's tiny. So there is this further suppression by mass hierarchies. Okay. Yeah. So now let's take a closer look at the observables that with which we can measure these CP violation in the standard model flavor processes. And in particular, we'll start with Cp evaluation in neutral meson mixing. So. And for simplicity, we'll focus on the B sub D system, and then later we'll generalize to all the other two neutral meson systems. So we'll start with the B sub D system. In particular, the B0 neutral meson will correspond to a Flavour eigenstate, a bound Flavour eigenstate of B bar D. And whenever I will denote B0 bar, this will mean the Flavour eigenstate with Flavour numbers B, D bar. Okay? Now these are, of course, not Cp eigenstates. And we can denote the Cp transformation properties of B naught and B naught bar. So a Cp transformation on B naught will in general give B naught bar, but of course up to a phase. So let's denote this phase as e to the I psi B. And then similarly, Cp transformation on B naught bar state will give e to the minus I psi B times B naught state. Now, with these definitions, we can write down the time evolution of a general admixture of these Flavour eigenstates. So we start at time equals 0. Let's say at the time of production or fragmentation of a state, and so let's denote this as the state psi of 0, where this is the time 0. Okay, and in general, this will be an admixture of the B naught and B naught bar. So I can parameterize this state as with some coefficients A of 0 times B naught state plus B of 0 times the B naught bar state. Okay? After some time t, I can write my state psi of t as A of t times B naught plus B of t times B naught, but since B mesons decay, this is not yet a unitary evolution, so I need to add a series of final states into which the B and B naught can decay. So this will be then parameterized by, for example, C1 of t times some decay final state F1 plus C2 of t times the final state F2, and so forth. If I want to discuss Cp evaluation in meson mixing, I'm basically only interested in the B naught bar system, which is not a unitary time evolution system, but I can still parameterize its time evolution. Okay? So I'll be only interested, right now, I'll be only interested in the evolution of A and B, time evolution of A and B. So let me just, so you don't forget, these are B naught bar decay products. Okay. Okay, so if we are only interested in the evolution of A and B, we have a two-state system. And I can parameterize the time evolution with a non-unitary, non-Hermitian Hamiltonian, which I can split now into its Hermitian and anti-Hermitian part, which I will denote as with M and gamma, and it's conventionally parameterized in this way, where M and gamma are time-independent and Hermitian 2x2 matrices. And M will, in practice, parameterize dispersive contributions to the time evolution. So this will be dispersive. And will be, so it will contain all the contributions from all possible off-shell intermediate states. And will parameterize the unitary evolution of a stable, would parameterize unitary evolution of a stable BB bar system. And gamma is usually denoted as the absorptive part. Absorptive part of the Hamiltonian, and contains contributions from on-shell intermediate states. So basically, rescattering of B bar decay products. And parameterizes the non-unitary evolution due to decays of B and B bar system. So now I can write down the Schrödinger equation for this system of coefficients. So AT, A of t and B of t. And this will be given just by the Hamiltonian acting on these two time evolution coefficients. So I can search for, now I can search for the eigenvectors of this. And I will denote the eigenvectors as B, L, and H as the light and heavy mass eigenstate of the Hamiltonian, both of which would be a linear combination of the Flavour eigenstates. So I can write this as some PLH of B naught plus some Q, L, or H, that's B naught bar. And I require, of course, that PLH squared plus QLH squared equals 1. Now this would hold, so I would have this would be the only constraints I have for a general H, general Hermitian H and gamma. Of course, I can use a further ingredient, namely constraints from CPT. In presence of CPT, it requires that M11 equals M22, so the diagonal entries of both M and gamma have to be the same. So if M11 equals M22, and also gamma 11 equals gamma 22. And this leads to a further constraint then that this expansion or parameterization coefficients P and Q have to be the same for L and H. So PL equals PH, so I can drop the subscript and I will denote this just with P. And similarly, QL has to be equal to QH, and I will just denote it as Q. So this will be my definition of P and Q. Finally, if there was also Cp invariance, which we know it's not true in the standard model, but in the limit of Cp invariance, one can show also that the phase of M12 has to be equal to the phase of gamma 12. And this leads to the constraint that absolute value of Q over P has to be equal to 1. Okay. And again, this is only true in the limit of Cp conservation. Okay. Yeah. Sorry? Oh, thank you. It could be that I missed the... Yeah, exactly. Sorry. I forgot. Yeah. Thank you. Yeah, of course. Yeah. Okay. Yeah, so to put it differently, if there was Cp conservation, then I could always write B and B bar in terms of Cp eigenstates, which would be just B plus minus, B naught plus minus B naught bar, okay, up to a phase. This would be this condition, Q over P equals 1. Now I will define, so this is still in terms of, in principle, unmeasurable quantities. So let me define a couple of measurable quantities to reparameterize this. So I will define the following thing. I will define small m as the average mass of the heavy and light state, eigenstate. So this will be ml plus mh over 2. And similarly, I will define gamma as the average decay width of the heavy and the light eigenstate. And then I will define the orthogonal quantities, which will be the delta m, which I'll define as the difference between the heavy and the light mass, okay, which is defined as being always positive. And I will define delta gamma as being the difference between the decay rate, the decay width of the heavy and the light. So delta gamma can have any sign, because we don't know if the heavy state is longer or shorter lived than the light one. Also, I will not use them, but in the literature you will also find related quantities, which are sometimes denoted as x, which is just delta m over gamma, and y, which is defined as delta gamma over 2 gamma. Okay. Now let's reconsider the time evolution of our system in terms of these measurable quantities. Okay, these are just by measuring the two masses and the widths of, or lifetimes of the physical mass eigenstates, I can parameterize this time evolution in terms of these quantities. So the time evolution can be written as following, and I will denote the following. I will denote B naught of t state. This will be a state which started out at t equals 0 as a B naught. This will be pure B naught Flavour eigenstate at t equals 0. And similarly, I will define B naught bar of t as the state which started out as pure B naught bar flavor eigenstate at t equals 0. Okay. With these, I can now, okay, maybe write it here. With these definitions, I can now write out the time evolution of, so the B naught of t and B naught bar of t. In particular, I can write B naught of t in terms of two functions, g plus of t times B naught minus q over p times g minus t times B naught bar. And similarly, the state B naught bar of t can be written as g plus of t times B naught bar state minus q over p times g minus of t times B naught. And both g plus minus time evolution functions can now be written out in terms of measurable quantities, and they are defined as 1/2 times e to the minus I m heavy t minus 1/2 gamma heavy t plus minus e to the minus I m light t minus 1/2 gamma light t. Finally, these states after some time t will decay. Okay? So, and we never observe the B and B naught, but we only observe the decay products. So the next step is to parameterize the decay amplitudes. So these states will decay to some final state f after time t. And we can parameterize the decay amplitudes in the following way. A decay amplitude of the state B naught I will define as just A subscript F. Similarly, the decay amplitude of the same state B naught to a F bar, so Cp conjugate, F bar, I will define it as A F bar. And similarly, the decay amplitude of the B0 bar decay to the same state F will be labeled with AF, but a bar on the A. Okay? So a bar on the subscript denotes that it's decaying to the Cp conjugate final state. A bar on the A denotes that it's actually the B bar state, which is decaying. So now you can already guess how I parameterize the decay of the B naught bar state into the F bar. This will be given by A bar, F bar. Okay. Okay. So now I can write down a time-dependent decay rate of a state which started out at time equals 0 as a B or a B bar, and then decay to a final state F or F bar after some time t. So I can write down time-dependent decay rate, d gamma of, let's say, B naught of 0. So this is a state started out as B naught at time equals 0 and ended up after time equal t in the state F of t. Per unit of time. And I can parameterize this in the following way. So there will be an overall normalization factor, which I will not care about. I will just parameterize it at n naught, which will basically be just the flux normalization, how many B's I start with. Then I have the overall e to the minus gamma t factor, where the gamma is now the average decay width of the light and heavy state, times the absolute value of AF squared, where AF is just the uppermost amplitude, times the following expression, which is a bit lengthy, but one has to write it out at least once. Okay? And I can parameterize it in the following way. In complete generality, 1 plus the absolute value of a quantity I define as lambda f over 2 times cosine hyperbolicus delta gamma t over 2 plus 1 minus the same quantity lambda f squared, absolute squared, over half cosine delta m t plus the real part of this lambda f times sine hyperbolic delta gamma t over half minus imaginary part of lambda f times the sine of delta m t. So what is this lambda f? Lambda f is just the ratio of decay amplitudes of B and B bar state decaying to f, since I'm looking at the final state f, weighted by the mixing parameters of BB bar system, so Q over P. So this is defined, lambda f is here defined as Q over P times A bar f over AF. Okay? So this was for evolution of B naught to F, and we can write down, so we have, in general we'll have 3 such expressions. I will not write down 4 such expressions. So B naught to F, B naught bar to F, B naught to F bar, and B naught bar to F bar. I will not write down all of them. I will just write down the second one, and then the third and the fourth you can derive on your own. But it will be obvious how you go about. So I will just write down this similar expression for a time evolution of B naught bar to the same F of t. So a similar expression for d gamma of the B naught bar of 0 state to f of t per unit of time will be given, of course, by the same flux the same overall factor minus gamma e to the minus gamma t. And now I normalize everything to a bar f, decay amplitude absolute squared, times, again, a time evolution expression, which is now given by 1 plus lambda bar f absolute squared over half time cosine hyperbolic delta gamma t over 2 plus 1 minus absolute lambda bar f squared over half time cosine delta mt plus the two interference terms, we'll discuss them in a minute, lambda bar f, real part of lambda bar f times the sine hyperbolic delta gamma t over 2 minus the imaginary part of lambda bar f times the sine delta m t. There is one big bracket missing here. And again, I've just defined lambda bar f as p over q times af over a bar f. So it's basically just 1 over lambda f. Okay? And now, of course, these are the two expressions. Now you can derive or guess, I guess, the similar expressions for decays to final state f bar. It's trivial by now. So, analogously for decays to f bar. Okay, so let's finish this lecture by discussing a bit the physical implications of these expressions. So what they mean in terms of observable quantities. So the terms which are proportional just to the AF and A bar F respectively, so without these lambda factors, they would actually correspond to the decay without mixing. Okay, so basically, just in this case, a B naught state evolved, and when it decayed, it was the B naught. Okay, because it decayed with the decay amplitude AF, which parameterizes the decay of a B naught state. The terms proportional to lambda F squared parameterize the cases where a B naught evolved to a B naught bar and then decayed, because it's parameterized by the A bar F decay amplitude. So these are these two first terms. Then we have two additional terms which parameterize the interference between these two possibilities. Okay. So you will see that the Cp violation, the presence of Cp violation, is signaled by a single term in this expression, and it's this last term. Okay? It's the only term which is sensitive to the presence of a phase in either Q over P or F bar, A bar F over AF. Okay? So it's this last term that we want to extract if we want to probe Cp violation. Okay? Presence of Cp violation. In particular, this is perhaps most easily measured if F is itself a Cp eigenstate, such that F bar equals F. So this term, our Cp violation, can be observed in neutral B decays to Cp eigenstates. F, let's denote them with FCP. In this case, F and F bar are the same state, so we can write down the time-dependent Cp asymmetry, which we'll denote as A FCP of T, which is defined as this d gamma over dt of B naught bar at 0 to FCP at time t minus d gamma over dt of B naught 0 to FCP at t over d gamma over dt, so the sum of the two terms in the denominator, 0 to FCP of t plus d gamma over dt of B naught of 0 going to FCP of t. Now, plugging in the above expressions into this asymmetry definition, we can simplify the resulting expression a lot in a limit which is applicable for B sub d decays and to some degree to B sub s decays, but unfortunately not for kaon decays. In particular, in B and to some degree in the B sub s system, delta gamma is much, much smaller than delta m, and the absolute value of Q over P is to a good approximation, so down to, I think, 10 to the minus 3 equals to 1. Okay? So Q over P is just a phase in the B system, and we can drop the delta gamma terms in this time evolution. In this limit where we assume that Q over P is a phase and we drop delta gamma terms, then this AF Cp of T simplifies a lot and can be written just as a sum of two terms, SF times sine of delta m T minus CF times the cosine of delta m T, where SF is defined as 2 times imaginary part of lambda f over 1 plus absolute value lambda f squared, and CF is just 1 minus absolute value lambda f squared over 1 plus absolute value lambda f squared. Okay, this is Cp. Cp, and then all of this is Cp, if you want. Cp, 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 Cp. Okay? So in particular, this is precisely how this S psi k short is defined. It's exactly this thing. Okay? So the measurement of sine to beta is done using the time-dependent decay rate of neutral B mesons to a Cp eigenstate. The Cp eigenstate in this case is the state of a J psi and k short. Okay? And doing a time-dependent measurement, so extracting the time evolution of this decay rate, of this asymmetry, Cp asymmetry, time-dependent Cp asymmetry, extracting SF extracts exactly sine to beta. Okay? And let me stop here, and we'll continue after in the afternoon. So, are there any questions regarding? regarding this? No? Okay, so then we can finish a bit early.